Greetings all. Let's continue with our discussion of the Gram-Schmidt Orthogonalization Procedure. So kind of where we left off, we actually showed that if we had a set of vectors that had two elements in it, that we could construct an orthonormal set from that. And so the idea basically is that we're just going to induct on the dimension of the space, so how many vectors that we've got in that set. And so if we suppose for a set of size n that we can find an orthonormal set, then such that the span of v1 up to vn is equal to the span of our orthonormal set w1 up to wn. So let's suppose that we've got a set of size n plus 1, okay, that this is going to be our basis set. Well, since these are linearly independent and span the entire space, then v1 up to vn form a basis set, and those things trivially span the space of the span of that set, so v1 up to vn. And so by our induction hypothesis, we can come up with an orthonormal set w1 up to wn that's equal, whose span is equal to the span of v1 up to vn. So now the idea is that we take v sub n plus 1 that's not in that span. It can't be in that span because the set v1 up to v sub n plus 1 were linearly independent. If it were in that span, then it means some linear combination of these guys gives us v sub n plus 1, but then moving things over, we would get a linear combination that gives us 0. That can't happen. And so v sub n plus 1 can't be in that span. So since it's not in that span, then it's not in the span of w sub 1 up to w sub n plus 1. And so if we take our projections, so we kind of do the same thing that we did before, we're going to take vector projections. We're going to take the projection in the direction of w sub I of v sub n plus 1. So these were just our dot products there. Then we subtract those projections from our original vector, and that gives us a u sub n plus 1. Now, since v sub n plus 1 is not in the span, this u sub n plus 1 can't be 0. If it were 0, then we just move this over to one side, and v sub n plus 1 is in the span. So that tells us that u sub n plus 1 can't be 0. Since it can't be 0, if we kind of take that one step further, and if we do the dot product with one of our w sub j's that we've already got, then this one, kind of doing the same thing as before, we replace with our description of what u sub n plus 1 is. Then we use our properties of our dot product, that these things distribute across addition. So we distribute across the addition, then we're using the linear part, and we can pull out these scalars to the outside. That's our w sub n plus 1, w sub I, leaving us with w sub j dotted with w sub I. Well, remember our properties of these guys, that they were 0 if I was not equal to j, and 1 if I was equal to j. So this whole expression, all of the terms cancel out except the one for w sub j. So again, what happened as before, by the symmetry of our dot product, those guys cancel out and we get 0. So our u sub n plus 1 is going to be orthogonal to all of our w sub j's. So last step we do from there, we just normalize. So we divide by the square root of the length, or we divide by the square root of the dot product of u sub n plus 1 with itself. This becomes our w sub n plus 1. We take that new w sub n plus 1, put it into our set with our previous w sub n, and now what we have is that v sub n plus 1, if we replace those, gives us a linear combination that yields our v sub n plus 1. Kind of rearranging things, we have this expression. So that tells us that v sub n plus 1 is in the span of w1 up to w sub n plus 1. And so our span of w sub 1 up to n is equal to our span of V1 up to Vn. So we throw in a new vector that's also in the span, and so our resulting spans have to be equal. And so we have come up with this new vector, a new set of vectors that do span the original space, and that was exactly what we were looking for. Now this kind of procedure of you start with your first vector, you normalize that, and you take the projection, you take away the projection of the second vector onto the first vector, you throw that part away, gives you something orthogonal, normalize that, move on to the third one, take away the projection onto the first two, and so on and so on and so on, and you eventually get, with that procedure, an orthonormal basis for the set that you were originally given. And so kind of putting all of that together, it is possible to take this original set, apply this Gram-Schmidt orthogonalization procedure, and come up with an orthonormal basis set for your space. So we'll take this one, we'll apply it in our next discussion of eigenvalues and eigenvectors, and I will see you guys then.